sheet front and back on every exam. So you can bring a note sheet front and back to each exam, okay? I stopped allowing you to use all your notes because everybody kept just bringing 30, 50 pages of notes, and then they wouldn't get any questions done because they'd be sitting there flipping notes, right? So stop doing that. Front and back, one page of notes. Okay, now, so you're going to, number one, determine the units your final answer needs to be in. Establish the given information. Decide how to set up the problem, which conversion factor needs to be used to leave the desired unit in the answer. Typically, this is going to be the desired unit on the top and the given unit on the bottom. Because if you do it the reverse way, you're going to get 1 over what you want. And so you'll get a flipped units, right? So you always want to try to line up your desired unit you want to end up in on the top. The things that you can cancel, because you know you can cancel them, are usually best on the top. Okay? Then you're going to solve your problem. This is a pretty good overall trajectory to dimensional analysis. Realistically speaking, you can solve a 20 to 50 step dimensional analysis problem just by doing this over and over and over. Okay? Taking it one deal at a time. And you'll get it eventually. Most chemistry problems are actually just pretty simple dimensional analysis problems with a little bit of definitions and a little bit of understanding what you're looking at. Okay? Mathematically, most chemistry problems are not super complex, right? So, significant figures. These are going to be measurements of matter. It's going to rely on your precision of your instruments that we use to measure it and the precision of your process used to measure it. It's important to report the calculated answers reasonably. If I have something that I just loosely measured and then I say that it's accurate to 0.00000001, does that tell you that I just loosely eyeballed it? No, you're going to think I really measured that accurate, right? And I'd be lying to you then, wouldn't I? Because I did not. Okay? And so you really need to be careful about presenting your data as accurately as you actually measured it. Okay? Significant figures is actually going to be how you do this in the lower end of chemistry, and it's sort of the quick and easy intro to that, okay? We won't go to the higher level, but if you ever want to go into sciences, you'll go into that higher level, okay? Most of you don't really need to know that. You just need to know sig fig level of stuff, and you'll be good. Now, when reading a measurement from a non-digital device, there's going to be some level of uncertainty in that measurement. There's always some level of uncertainty in any measurement. You can never be 100% accurate. That's just impossible. However, a digital device is just going to tell you straight out what that number's accuracy is to some degree, okay? Because the digital device is just going to give you a number with decimal places, right? So it'll give you something like 1.01, okay? Well, my uncertainty's right there, isn't it? That's where the number ends. And it doesn't trip me up. I'm not going to go, oh, do I put this? I didn't give me that, did it? And so it's less likely to trip people up, okay? However, if you are given a non-digital measurement that you have to actually measure using markings on, say, a ruler, well, it becomes much more questionable then, doesn't it? What would this be? That's halfway in between, isn't it? Yeah. And so I can actually guesstimate one more, can't I? I'm actually not uncertain about this measurement here, am I? It's past that. 100% past that. No uncertainty at all. I'm uncertain about halfway in between that. Okay? And that's the difference between a digital and an analog measurement. Digital measurements will give you that last digit for you, and you don't have to think about it. Analog measurements, you have to think about a little bit. Okay, in any measurement, all non-zero numbers are going to be considered significant. So anything that's a non-zero is always significant, okay? Because you wouldn't put it there if it wasn't significant. All right, let's talk about significant figures that are zeros. Now, zeros can sometimes be placeholders, can't they? If I write out 100, I have to put 2 zeros, don't I? I don't have a choice. So are those significant zeros? No, they don't have to be, do they? It could just be loosely, I measured it to the hundreds, okay? Like, you probably know your bank account somewhere to like the tens or hundreds, right? But you probably don't know your bank account to the pennies, do you? Okay. And so the zeros tend to be our troublemakers whenever we're learning this, whenever we're discussing this, because their significance does depend on the position and how they're written in. If a zero is a number without a decimal point is significant, that can be shown by putting a decimal point after that zero. And so, for example, if I write out 100, no decimal point at all, those zeros are not significant. I'm just putting them there because they're placeholders. Okay? Not significant. My significant digit is the 1, right there. And what that means is I'm estimating to that hundreds place. Okay? I could have $80 in my bank account, and I have like $100. Okay? Now, if I were to put this with a period behind it, that now becomes significant. I've looked at my bank account, I didn't count the pennies, and I went, I have $100, okay? And if I had had $101, I would have written it like that. And it would be 101, right? I'm not estimating that last digit, okay? I've actually read it. All right. So my uncertainty is in that last digit. I could have 99.9, and I rounded it into 100. Okay? But I'm very, very close to 100. I'm within pennies of that. Is that making sense so far? Okay. Is money working for all of you to understand this? All right, so let's talk a bit about exact numbers. Now, numbers that are used in defined conversion factors and counted items are exact numbers. These have an infinite number of significant figures. One of the examples of exact numbers is like the number of people in this classroom. We can exactly count it, right? And so how sure are we? We're very sure. We're 100% certain there is no partial person, right? We have that many people, period, good, go. Now, the other thing you can get exact numbers on is definitions. Definitions are a lot of the exact numbers you're going to encounter. For example, when we talked about a centimeter versus a meter, right? That's a definition. There has to be 100 centimeters to make a meter, period, all the time, okay? It can never be 99 centimeters make a meter. That's just not how it's defined, right? So definitions are almost always exact numbers. A lot of these unit conversions we're going to look at are going to be exact numbers. However, there are unit conversions that are not. Okay? It's a pretty easy way to know this actually, because it's usually not numbers that have zeros at the end. So you have these like very strange 2.54 ... numbers. That's centimeters to inches, by the way. And that's because they're not exact numbers. Okay? They actually do have error in them. All right. Okay. So let's look at some examples of this. A digit is significant if it's a non-zero. These are all non-zero numbers. So these are the number of significant figures in each of those numbers. Okay? And so here we have 1, 2 significant figures. This right here means we have 2 sig figs. Is everybody okay with me saying sig figs? And connecting it back? Very good. Okay, this one has 3 significant figures, and that's just 1, 2, 3 here. Everybody say that okay? All right. Notice that this has a 0 between significant figures, and so that 0 always has to be significant. Okay? And so 101 this is 3 sig figs. 6.071, this is 4 significant figures. Now notice that every single number must always have the number itself, sig figs, where it's uncertain, and then it has to have the units, right? Without the units, the number doesn't actually make any sense, okay? So if I say I weigh 1, is that a lot or a little? Depends, doesn't it? Yeah. If I weigh 1 son, that's a lot. If I weigh 1 gram, it's very, very small. Yeah. Okay. And so a 0 at the end of a number with a decimal place, those are also significant. And so we have 20 period, and that is 2 significant figures. Here we have 9.800, that is 4 significant figures. Is everybody okay with those examples so far? Right. Now, a 0 not being significant, these are called typically placeholder zeros. They're there because you can't write the number without them, okay? And so they are not significant. They have nothing to do with uncertainty. They're there because I can't write that without it, okay? And so we have 0.03 that has 1 significant figure, which is that 3 right there. These other 2 zeros, they're just there so I can write the number, aren't they? All right. Can everybody see that okay? Okay. This one also, these are numbers that are before the significant number with decimal places, okay? Whenever you do these, what you're going to do is you're going to find your decimal place, and then whenever you get a significant figure, that's where you start counting. So right here, we start counting at the 2, 2, 4. Okay? All right. So let's say that we had something like, how many sig figs? 1, 2, 3, 4. And these are significant because they are sandwiched in between, right? Okay. How about same number of sig figs, isn't it? Yeah, 4 sig figs. And again, we start right here. That's our 1, right? First sig fig, second, third. Okay. Now, whenever you have a decimal place, let's say I had instead all right. Let's say I had instead this right here. How many sig figs? Ooh, tough one, right? So this one, not significant figure, right? Not. This one's a significant figure, isn't it? Now, because we have a decimal place, everything to the right of that becomes significant. I don't have to write these zeros to have the same number, do I? No. So those were intentional, and they're significant. Okay? And so that was 4 sig figs again. I wrote that to tell you that I measured it, and I measured down to this place right here, and that's where my uncertainty is. So that one could go up or down a bit, right? Does that start to make a bit of sense? Now remember that when you're looking at significant figures, they're very intentionally a measure of uncertainty. How certain is that number? Where is my error in that number? Okay? Okay, so let's talk about using these in calculations, all right? So if we add, subtract, multiply, or divide, these can result in numbers that have more certain than they are or less certain than they are. Manipulating measurements with arithmetic cannot increase the certainty. So you can't become more certain in a number just because you did arithmetic, okay? So let's say I'm sitting there and doing some multiplications. And I'm putting a bunch of numbers in. 9.99 times 9.9 times 9, okay? And I sit there and multiply these numbers. My calculator is going to give me something, and it's going to be, I don't even know what this is, I don't care. Let's say it's 9.9999999. and it has this extending decimal sign, right? So the calculator stops having numbers in the window. Okay. It didn't make it more certain, right? The calculator doesn't know uncertainty, and so it just messed up it. Okay? So when you get these numbers that go all the way out to the end of your window or vastly increase the number of decimal places in your calculator, understand that those are not increasing your certainty, right? Okay? And what I'm going to teach you here is how to figure out where that certainty actually is. In this case, we would have one significant figure here. That's our lowest number of significant figures. And so we would actually end right here. That would be our number of sig figs, 1. Okay? We would round this using our rounding rules, in which case that's going to be 10. Okay? Notice I very intentionally didn't put a decimal place, because how many sig figs do I want? 1, right? All right. It's a little preview. Okay, so an answer can be no more certain than the least certain number in its calculation. Now, notice I'm being intentionally vague at this point right here. Okay? And that's because the rules for addition and subtraction are a little bit different than multiplication and addition. Okay? And it's because they transform your numbers differently. Now, let's talk about the rules real quick. The addition subtraction, these answers should match the least number of decimal places in your measured numbers. Let's do a really easy thought experiment when we're done with this part, and you'll very quickly understand why. Okay? So multiplication, division, these have to match the least number of significant digits in the measured numbers. Did everybody see the difference between those definitions? So multiplication, division, number of sig figs, right? And addition, subtraction, number of decimal places. Okay? Okay, so think about it this way. If I added 0.1 to your bank account, is that going to change the ones number much? No, it's going to make almost no difference to the bank account, right? And so, in fact, I can add such a small amount that it's just going to be rounded off, right? If I added 0.000001, the bank actually just rounds that down and keeps that. They don't even give it to you. Okay? Anybody seen the Superman virus? No, there's a virus that's been used, as far as I know, it's been used about 6 times now. The last time a Ukrainian group stole, I think it was $600 million from a banking chain. And what it does is it takes all the calculations that the bank does, and it just takes, after the significant figures, chops that number off and puts in an account. And so every calculation the bank does, it takes like a millionth of that transaction. And if you do that trillions of times a day, you make a lot of money really fast, right? Okay. And so it was actually the plot in a Superman movie. And so people tend to call it the Superman virus. Because that was actually based on a real hacker group that did that again. And exploited ATMs up again, I believe. Yeah. So if I add a small or subtract a small enough number, it's just not going to matter, is it? It's going to be meaningless. I won't even bother. I'll just round it off. Okay. But what if I multiply an extremely small number? If I multiplied your bank account by 0.0001, are you going to be happy at the end of that? No. Your bank account's going to go from, let's say you had $1 million in it, your bank account's going to go like $10, right? Yeah. Poof, money's gone. And so multiplication, very small and very large numbers, are extremely meaningful, right? And that's why we use sig figs. Because you notice the number of sig figs doesn't really matter how big or small the number is, does it? Okay. All right, so let's talk about the rules for rounding numbers. Now, this book is actually slightly wrong in how it tells you to round numbers. Okay? And I want you to tell me if this is how you've learned to round numbers. Okay? So, if the leftmost digit to be dropped, the one following your last retained significant figure, is 4 or less, Simply remove it and the remaining digits. That's correct. Okay, that's fine. Is that how everybody knows it? Okay. If the leftmost digit to be dropped is 5 or greater, increase the retaining digit by 1 and remove all other digits. That's the one that's wrong. Okay. Who here learned it that way? Everybody? Don't be like embarrassed or anything. It's from what I can tell, this is like how they teach it now in algebra and stuff, which it is just, it's wrong. But for most of you, it's not going to matter that much unless you go into anything that your job's actually important, in which case it'll matter tremendously and you're going to screw somebody out of a lot of money. Excuse me for the language. You know that there's somebody that actually ended up causing tens of millions of dollars of damage to their business by doing this. Yeah. And or to people, actually. Somebody at a bank did this to the person, and they actually robbed tens of millions of dollars from people. So if a rounding of a large number with no decimal place, substitute zeros for numbers that are not significant. So go ahead and just use this for this one. But when you're in the real world, if you're doing anything real world, know that this is wrong. And I'm going to tell you the correct way of doing this. Okay. The correct way to do this is this rule is correct. That's fine. So if it's 4 or less, you go ahead and round it down. Okay. If it's 6 or more, you round it up. Right. If it's 5, you actually need to round it evenly both ways. Right. So let's say you're working on 100 different numbers and you're doing this, right? If you round it up every time you hit a 5, well, 5 is the exact middle, isn't it? Everybody see that? It's not actually on the bottom or the upper end. It's the exact middle, actually. Okay? And so when you're working with many times where you're doing like rounding over and over, if you always round this up, then your number's always high, isn't it? Okay. And so what you want to do is if it's an even number, you round it down. If it's an odd number in front of it, you round it up. That's typically how you handle that. Mm-hmm.
Can you do like an example of the 5, like rounding up?
Mm-hmm. Yeah. So let's go ahead and go. Okay. Let's say I want to round this to the tens place. Okay. And so according to them, I'm going to round this up to 60. Okay. And then that's how I would write that. That making sense? Okay. Or like 95. Actually, let's avoid that one. It's going to end up causing issues. Let's say I'm doing that. Okay. So that's what my calculator gave. I'm supposed to have 2 sig bits. And so what I do is I'm going to round this up to a 6. And now I'm going to have 2 significant figures. And for this class, fine. Not a problem. It's not going to damage anyone you doing that, okay? So, totally fine. However, I want you to know that if you go out into the business world, if you go out into the science world, if you go out really anywhere where you're handling numbers at all, don't do this, okay? It's going to cause problems because you're always going to be high and you're often going to be compounding that mistake over and over and over, okay? And so the correct way to do this would be so this one would round down, this one would round up. Okay? That's actually a much more correct way of doing it. Okay? If you actually have the opportunity, it's better to do this where you literally round up one time, round down one time, and even it out. Okay? Over and over, just even it out. But oftentimes you're not going to have that, so you won't know what your next number is going to be, right? So, but it really does matter. Okay, it's caused tens of millions of dollars in damages, and The last estimate I saw ranked that every $40,000 of damage actually causes somebody's life to be ruined. So, like, hundreds of people had their lives altered in ways that they did not want altered. Okay, so it's actually a big deal. Okay, let's talk about scientific notation. Has everybody encountered scientific notation before? Okay, so you take your coefficient right here, this is the coefficient, times 10 to some power, okay? And that power right here is going to represent what decimal place you want to be in, okay? All right, so this needs to be a number right here that is greater than 1 but less than 10 for this coefficient. Will you see numbers that are greater than 10 and less than 1? Yes. Yes, people will do that just because they want to compare it to other numbers, okay? But correctly said, scientific notation should have greater than 1, less than 10. And any of those things that would have been less than 1, greater than 10, you take that decimal place out into here, okay? Now, this exponent right here is going to tell us what tens place we actually are in, okay? So a positive exponent tells us that we have a number that's greater than 1. So for example, if this is 10 to the first, we're in the tens place, aren't we? 10 to the second, hundreds, 10 to the third, thousands, okay? A negative exponent tells us the number is between 0 and 1. For example, 10 to the negative 1, that's that first decimal place, the tenths, isn't it? And then 10 to the negative 2, that's the hundredth decimal place, isn't it? So 0.01 sort of numbers, okay? Scientific notation, only significant figures are going to be shown in the coefficient. And so once you have to start using significant figures, you're going to find that this is the preferred way to do it because your life just becomes so much easier, right? Yeah. And you always kind of know the number of significant figures in a scientific notation because this is always 1 up to 9 something. And then you go the decimal places and wherever it stops, sig figs, right? So your life becomes so much easier. And that's why it's typically called scientific notation, because scientists need to work on significant figures. And so we really like this, don't we? Yeah. And also it decreases the number of numbers we have to write out on. This right here is the meaning. These are the scientific notations. Does anybody have any questions about that? Okay, notice it's literally just different ways of writing the number, right? This right here means that it's 1 over is the negative sign. So that negative tells you that. And then the 6 right here tells you there are 6 tenses multiplying each other. Everybody say that okay? Okay. This right here, no negative sign, so it tells you it's in the numerator. And there's 6 tens multiplying each other, right? Okay. Another way of saying that is that you have the 6 zeros, don't you? For a million. Okay, let's talk about percents. Percentages are always parts of a whole times 100%. So you take part divided by whole and then times 100. Another way of saying percent would be parts per 100. Anybody ever heard parts per million, parts per billion? No? Oh, your water must be clean. No lead contamination tests. So yeah, that's what you'd get, like a water contamination would be in a parts per million, parts per billion. Okay. And the only difference there would it be times a million times a billion here. Right. This is parts per 100, so it's times 100. Okay. So percent. Everybody's seen percentages before? Okay, fantastic. Be very careful about using your calculator's percentage button. People get confused by that a lot and then get messed up. Okay? It's usually better just to do it in your own head and avoid that percent button on your calculators. So again, if you have a percentage, that means to get it out of percentage into a decimal format, you have to divide by 100, don't you? Okay. I think everybody's probably good there. Mass. This is anything that takes up space that can also be placed on a scale and weighed. Mass is going to measure the amount of a material in an object. This is a pretty decent definition. This one right here is actually a circular definition, but people tend to kind of understand it easier. Now, a common unit for mass is going to be things like gram. The weight of an object is going to be determined actually by the pull of gravity on that object. That force actually changes depending on the location. In fact, you can change the location just if you were to drive across California, you'd actually get different masses because gravity and magnetics actually change as you move around California. It's actually quite notorious for that. And there's a lot of like high-grade labs. So it's really well known. Now, that is dependent on gravity. So if you go up to the moon, does anybody know what happens to your weight? And gravity goes down a lot, and so you have a lot less weight, about a tenth-ish. So if you went to like closer to the sun, you'd actually weigh more, a lot more. Okay. Mass does not change. So mass would not change. Mass is actually independent of gravity, but is acted upon by gravity. Okay. So as long as an object is weighed in roughly the same location on Earth's surface, or you have a correction for it, the mass and weight will have the same measured values. And so you can actually use weight for mass. That's why we typically use weight for mass on Earth, is because our balances actually have corrections they apply if somebody's calibrated it. Nobody's calibrated it then. Too bad. It's not going to be the same. Okay, the volume. This is going to be a three-dimensional measure of the space occupied by the matter. Typically, it's represented in some way that would be a width, length, height multiplied by each other, right? Same as the volume of a cube. In the lab, the volumes are going to be routinely measured by graduated cylinder or pipettes. These are graduated cylinder. This is a syringe, which is a type of pipette. There are other types. These are other volume measuring tools. The unit is typically going to be the milliliter, which is 1,000th of a liter, because usually you don't want to work in full liter amounts. Okay, liter amounts are just too big. This should be pretty close to a liter right here. The typical unit in the clinical setting is actually usually cubic centimeters, cc, or cm to the third, which is also cubic centimeter. They're the same thing, actually. This is actually the exact same amount of fluid as a milliliter. Okay? So milliliters and cc's are actually the same thing. Right? 1 milliliter is going to be 1 cubic centimeter, and that's 5 milliliters is going to be a teaspoon. So if you ever see a teaspoon in your measuring equipment, when you end up needing a 5 milliliter, that's the same. Okay. Density. This is going to be represented by lower d for its one-letter designation. It's actually going to be a comparison unit. So we're going to take the mass divided by the volume. Okay, and that's density. What's that? Okay, so in the future, I'm not actually going to go back for you to write stuff. What you'll want to do is go onto the PowerPoints and print those off, okay? Okay. Or like represent that, hey, I still need that part of the slide. Right. Okay. Okay, so density, this is going to be a measurement, a comparison between mass and volume. So mass divided by volume. And you'll see density quite often. Typically, you would see the density of water, which is about 1.00 grams per milliliter. Okay. And that's the density of water. Now, there's also another unit called specific gravity that we'll get into just a bit, which determines whether something floats or sinks in water. Okay? And all it is the comparison of density versus water, right? So if something's more dense than water, it sinks. If something's less dense than the water, it floats. And there you go. That's also true for air, by the way. That's like why hot air rises. It actually becomes less dense. Okay? The volume actually increases for hot air, and so its density goes down, and it floats. That's why you can do like helium in a balloon as well. Helium is less dense than the air around it, and so it floats. Specific gravity. So liquid density specifically is very often used in this because you typically want to know is it going to float or sink in water. Okay. Solids are also sometimes done with this, but liquid density especially. The density of water is 1.00 grams per milliliter at 4 degrees Celsius. That is very close to that value at body temperature. It doesn't actually change that much from heating and warming, but it does change a bit. Okay. And so the ratio of the density of a sample to the density of water is actually going to be referred to as specific gravity. And that is SPGR. And what it is it's just the density of whatever sample you're looking at divided by the density of water. Okay. If it's 1, then it's going to kind of bob around somewhere in the middle-ish of the water. Okay. If it's less than 1, it's going to float on top. If it's greater than 1, it's going to sink. And that's actually how you get yourself to float. You take in air, increase your volume, you're actually changing your specific gravity versus the water, right? I know. Okay. The specific gravity of a liquid, this can actually be measured with a simple instrument. It's called a refractometer. Notice, by the way, the specific gravity, because you're using the exact same units on the top and bottom, does not have units. You actually have canceled all the units out. Okay? And so it's actually going to end up just straight up ratio. No units. You just denote, hey, this is specific gravity. So the temperature, we actually measure the temperature of a substance to determine its hotness or coldness is a decent way of sort of introducing your temperature. This is often done using a thermometer or electric temperature probes. In the United States, we use Fahrenheit, of course. In Europe, and almost everywhere else, Celsius. There's 2 other countries, if I remember correctly, that use Fahrenheit. That's it. Scientists actually use a different scale usually, and this is the Kelvin. And so a Fahrenheit and Celsius, have you everybody noticed that has a degree? So you say degree Celsius, degree Fahrenheit. Okay. And that's because those are relative scales. You're actually measuring in terms of Celsius off of the melting and boiling points of water. Okay. And so 0 Celsius is the freezing point of water or the melting point of water. Right? And so it's a relative scale, and that's why it's a degree. Okay. Kelvin is actually an absolute scale. And so 0 Kelvin literally means there is no heat energy anymore. The temperature is literally 0. Okay? And so that's absolute absence of what we would consider heat. Okay? Now, this definition here for temperature and hotness, coldness doesn't actually make any sense. You'll see it's a circular definition. It actually relates on itself. It never defines it, actually. If you're ever wondering what temperature and heat is, first off, coldness is just the absence of heat, right? Everybody knows that, right? Okay. So what heat and temperature actually are they a randomized kinetic energy? Okay. So everybody knows kinetic energy, right? You throw something and it has a certain amount of kinetic energy in that direction, right? And if you have 2 objects, well, those start canceling out, don't they? And so if you had millions of objects all going different speeds, all going different ways, a lot of them with different masses, this becomes ridiculous, right? There's no way of actually calculating the kinetic energy anymore. And so what we do is we sum it up as temperature, okay, or heat. And that's randomized kinetic energy. So again, the Kelvin is actually the SI unit. It is the one that is preferred in science. Does every scientist use it? No. Sometimes they put Celsius, almost never Fahrenheit, but every now and then. Temperature again. So again, we're going to have right here the different units compared to each other. Now what you'll notice is this right here is Fahrenheit. There's 180 degrees Fahrenheit difference between the freezing and boiling points of water. Okay? Water freezes at 32 degrees. It boils at 212 degrees Fahrenheit. You'll notice that this is the minimum temperature typically considered cooked. This right here is the temperature that your little car thing goes ding because you're looking at frozen stuff on the road, right? Technically, it does 34, but it's actually looking for 32 under bridges. Okay, that's when they're actually going ding, and you're going to encounter ice. This right here is Celsius. There's a 100 degrees Celsius difference between freezing and boiling water. Freezing water happens at 0 degrees Celsius. Boiling water happens at 100 degrees Celsius. Right here, you'll see in kelvins, that's a 100 Kelvin difference. But instead of water's freezing point being the 0, we actually have the 0 point being there is no heat energy. Okay? And so what that means is that when you're going between Celsius and Kelvin, you actually just add 273.15 to whatever your Celsius number is. Okay? If you're in Kelvin, you subtract that number to get Celsius. Okay. This is actually how I remember these things, by the way, which is kind of amusing. I remember that this 0 point right here is 32. And then I remember this 100 difference here is 180 here. And so I'm weird. This is the official formulas for these. So Kelvin right here equals Celsius plus 273. So if you have a Celsius number, you add 273. And that gives you Kelvin. Okay. If you want to go degrees Celsius from degrees Fahrenheit, what you do is you subtract off 32, and then you take that number and divide it by 1.8. If you want to go into Fahrenheit from Celsius, what you actually have to do here is you have to multiply that Celsius number by 1.8 and then add 32 to it. Because remember, 0 degrees Celsius is 32 Fahrenheit, right? So if you had a 0 there, it'd be 0 plus 32, and that'd give you 32 Fahrenheit. Okay. Again, these are on the website. If you ever want to get the PowerPoints, do it. They're also in your book as well. So. Body temperature. So the normal body temperature is 98.6 degrees Fahrenheit or 37 degrees Celsius. Note that you can have some wiggle room in your body temperature. Really, as long as it's below 100 degrees, you're going to be mostly okay. 99 degrees, you're starting to see some effects, but not much. Body temperature is going to vary from person to person. It's going to change every day. It is meant to vary to some degree. Haha. Sorry. Now, different organisms actually have a lot more variance in their body temperature. For example, cold-blooded can vary their body temperature much more, but like camels can actually vary it by 6 degrees difference, which you'll see here would be lethal to humans or most other animals. So if your human body temperature rises from 40 degrees Celsius or 104 degrees Fahrenheit, this is actually hyperthermia, that you're above temperature, hyper meaning above, right? Thermia, temperature, right? And this condition can actually cause convulsions, coma, or even permanent brain damage if you go long enough or high enough, okay? And so once you're getting close to 104 degrees Fahrenheit, that's the danger zones, okay? That's where you need to start actually lowering your temperature. Your body's overdoing it trying to fight that virus or that bacteria, okay? So aspirin's a good way to do that, or a cold towel on your brain will delay the worst of the effects because all of these are brain effects, okay? Whenever your temperature rises or lowers from that 98.6-ish, your enzymes become less efficient and your body doesn't work as well, okay? But you can withstand that damage a lot better than a small, tiny virus or bacteria. They don't have a lot of leeway in that. And so what you're doing is you're hurting yourself and them at the same time. Okay? And you're hoping you can outlast, which you usually can. The other way is body temperature drops below 35 degrees Celsius, 95 degrees Fahrenheit. That's actually hypothermia, Whoops. Typo. Hypothermia, HYPO, thermia. Okay? This is if your body temperature goes down. What you're going to start feeling is very cold, usually as your extremities first. because they're the ones that cool first. You'll begin getting a regular heartbeat and slow breathing. And realistically, actually, you can go pretty low for a long time as long as you don't actually damage your extremities and damage the flesh too much. Okay? So people can come back from actually pretty long periods of this, surprisingly so. Another interesting thing is this hyperthermia is actually pretty difficult to do to people unless they're sick. There's actually experiments where they've tested this at how long can people go. And really the longest one, the person just ran out of water. He put himself in an oven with a giant vat of water and a tube going to him. And you can take oven temperatures for multiple days and survive it. As long as you can replenish your water and as long as sweat is actually doing anything to lower your body temperature. Okay? So you'd be really impressed about the temperatures you can take. I know this for a fact because I used to work laying pipe in Utah and down near Las Vegas. And it would regularly be 140 out when I was out in the sun for 12 hours a day laying pipe. Okay? That was how I got through college. And so I would literally come out of places where it was more moist, the trenches where I'm laying pipe, and the water would go poof off of me in a cloud. It looked like I blew up. It was pretty wild. But you can take extremely high temperatures for an extremely long time. As a little side note, does anybody know which one has the higher death rate, hyperthermia or hypothermia? Huh? Yes, exactly correct. 5 times the death rate. Yeah, hypothermia is far more deadly than hyperthermia because we're very good at resisting hyperthermia. Okay. Energy. Energy is going to be the capacity to do work or supply heat. Stored energy is going to be called potential energy. Energy in motion is kinetic energy. Energy takes various forms, but is never created nor destroyed. It always has constant energy for the universe. Doesn't mean an object will have constant energy. It oftentimes loses energy to its surroundings. Energy, the law of conservation of energy is actually what this is right here. So energy is neither created nor destroyed. It is just transferred or transformed. Okay. The SI unit for energy is actually the joule, and that's capital J, joule. You'll oftentimes hear calorie. Notice this has a lowercase c. It's not the same as on the back of a package. Okay? And so lowercase c calorie. This is the amount of energy that's required to raise the temperature of 1 gram of water by 1 degree Celsius. And so 1 calorie actually equals 4.184 joules. And that's an equality that you can then use to do a conversion factor, right? Cool. Notice that those are what I'm giving you here is equalities that can be used as conversion factors if you need. The nutritional calorie is actually a capital C calorie. It's actually a kilocal. I don't know why they didn't just do kilocal. It would have made life easier. But that's the nutritional calorie. Capital C calorie is 1,000 times a actual calorie. Okay? So it's a kilocalorie. 1 capital C calorie equals 1,000 small c calories. Again, it was, I don't know why they made that decision. It was a bad decision. But heat and specific heat. So heat is going to be a kinetic energy. It's going to flow from a warmer body to a colder one. Note that heat, again, is a form of energy. All it is randomized kinetic energy. Okay? So every substance has the ability to absorb or lose heat as the temperature changes. It's going to change how fast that heat can transfer. You may have noticed, for example, like a piece of metal transfers heat a lot faster than a rag, right? And so when you lift a pan, ouch, hot, handle's hot, right? You take a rag on that same pan, not as hot, is it? Because the transfer of heat is slower. This is actually specific heat capacity or specific heat of a substance. And so it's the amount of heat that's needed to raise the temperature of 1 gram of that substance 1 degree Celsius. And so specific heat, which oftentimes is abbreviated SH, is the heat divided by the grams times the change in temperature. Okay. Now, metals have very low specific heat values, and so they heat up really fast, right? Water has very high specific heat values, and that's why the majority of energy in any economy is actually used in heating and cooling water. Did you guys know that? Yeah. Yeah. Because it has very large heat, specific heat capacity. So water liquid has a specific heat measured in calories of 1. You'll notice that literally the calorie definition was actually specific heat, wasn't it? Yeah. And so 1 calorie is 1 specific heat unit. Yeah. They just defined it in such a way that you're raising 1 gram of the substance, 1 degree Celsius, right? So that these units would be equal. Okay. Human body is a little bit lower than the water. We heat up a little bit faster than the water because we have bones, flesh, etc., right? Also salts in there. This right here, silver, gold. This is why gold and silver actually make very good heat conductors in copper. And that's why you see those inside of computers all the time. Okay? Transferring heat around. All right. Anybody have any questions about those so far? All right. States of matter. So a state of matter is going to be the physical form in which the matter exists. The 3 most common states of matter are going to be solid, liquid, and gas. And you guys all probably know these fairly well. There's solid, there's liquid, and there's gaseous water up here that you can't see. Okay. All right. Or the bubbles. Now, the state of matter, the particles in a solid are going to be orderly arranged. They're going to be tightly packed together, and they're going to only slightly move. Solids are going to have definite shape and volume. You can see this from your desk. It has definite shape and volume. Particles in a liquid are going to be less orderly and moving around freely. So a liquid is going to have a definite volume, but takes the shape of its container. You can all see this from that bottle right there. Would you mind waving your bottle? Thank you very much. And you can see how it conforms to the shape of the container, but has flow, right? So it expands to fill that container. Whereas the solid would not expand to fill that container, would it? It stays solid. The particles in a gas, these are going to have no orderly arrangement. They're far apart from each other, so they interact very little with each other. They're typically moving very fast past each other, so again, they don't have a lot of time to interact a lot. And so they're often going to collide with each other in the walls of the container, and so they will fully fill a container. It has no definite shape or volume, and it'll expand to fill the container in which it's placed. And you can kind of see that from the air around you. It, like if you went over there versus here, you still have that same air, don't you? Okay? Probably a better example is actually a fart. It expands to fill the entire container, and then everybody smells it, right? Okay. Again, this is a summary of what we just talked about. Right here, we're going to talk about accuracy and precision. These are going to be what involves in uncertainty. So measuring with accuracy means that you're taking a measurement that's close to the actual or true value of it, but you can be very far apart for each measurement. It just has to average to be that true value. Okay? Precision means that you're going to be taking measurements that are very similar in value, but they may not be close to the actual value. It could be like I'm using a tape measure, but the tape measure is wrong, right? Well, I'm going to get very precise values. I'm going to get the same value over and over, right? But if my tape measure is wrong, then I'm going to get very low accuracy, aren't I? Okay. So in taking measurements, it's best to measure with both accuracy and precision if you can. Accuracy is much more difficult to actually determine. Precision is usually pretty easy to determine. You just got to take more measurements, see if they're close together. This can be accomplished by taking measurements several times and averaging their values. This will help you with your precision tremendously and help you with your accuracy to some degree. Okay. These are units and dosing. So healthcare professionals use SI or metric units, but must be familiar with U.S. customary system of measurements and, of course, pharmacological measurements as well. So there's actually 4 different units. that can be used. And so these are the U.S. customary units right here. These are the SI or metric equivalent, and this is the U.S. customary equivalent unit right there. And then you also have pharmacological, which like are drips. Okay. Reading lab reports. Let's talk a little bit about that. Patient results are going to be given along with normal values. If you ever get your reports from like your blood testing, and you've seen those, you will have noticed this. If the result is out of range, it would be highlighted. Values are going to be listed as greater than 1, but this makes the units on the numbers vary widely. Most of the units are going to be metric, so you'll see a lot of things like a deciliter, and that's going to be equal to 1/10 of a liter, or 100 milliliters. Millimoles, which is going to be a 1/1000th of a mole. And so you often see like millimole over deciliter, and that'd be you'd see in your lab reports, okay, from your hospital. Okay, we'll pick up here next time. Hopefully I can gain some ground from all the tech issues. Anybody have any questions? And we'll get you with your, do you have your QR code yet? Okay. Bring your computer on up, and we'll, you all have a great day. See you Wednesday.
Are we gonna like go over any like multi-step dimensional analysis?
Yes.
Yeah. Those were on the like chapter 1 post.
So you have a few options. Go ahead and send me a, hey, this is the question I had difficulties with. I can send you a video. Come into my office hours. I can also do that. We'll also go a little bit more over some questions in the next one. But I didn't have prefixes introduced to the lecture yet, so I didn't do the problems.
So the chapter 2 post is on Wednesday.
Email me to have me double check. Email me to remind me to check it out, because we're running late due to all the technical issues we battled through.
Yeah, because like I did the chapter 1 post last night. Like I went through the book and stuff, and I was like, I don't know how to do like a lot of this.
Okay.
So I was just struggling.
Yeah, email me to remind me, and I'll check that out and move things around a bit. Okay. Okay, you have your computer on real